Hi, welcome to week 15 recitation for CEE222, and this will be our last recitation for this semester. So let's get started. Let's first look at the first problem, problem 7.3.5. The problem says we have a confined aquifer, have a transmissivity of 500 meters squared per day and the storage coefficient of 0.0005. Well, 1 and 2 completely penetrate this aquifer and will be pumped at a constant rate of 600 cubic meter per second, cubic meter per day, and 1,400 cubic meter per day, respectively. And we want to solve how long can the two well be pumped without exceeding a 1 meter drawdown limit in the observation well. So let's just have a really simple spatial diagram here. So we have well 1 and we have well 2. And we have the observation well in between, which have the distance 400 meter to the well 1 and have the distance equal to 500 meter to the well 2. And let's just write the rest of the information down here. The flow rate for the well 1 is 600 cubic meter per day, and the flow rate for the well 2 is 1,400 cubic meter per day. And we know that the transmissivity is 500 and the storage coefficient is 0.005. Okay, so how do we calculate the drawdown for this multiple well system? According to the equation 7.27 in the textbook, we know that we can linearly combine the drawdown of this caused by these two wells using the equation that I show here. So to use this equation, we will need to evaluate the value for the well function, which is a nonlinear function, and that function is determined by the coefficient u. Okay, so here I will not do the calculation for you, but I will explain the logic and show you the result table, and I hope you can do this on your own Excel worksheet. Okay, so we already know to calculate that, to calculate the drawdown, this is, we will need to calculate the use this equation and calculate the well function. The well function is the function of this coefficient u, and to calculate the coefficient u, this u is related to the time t. So the idea is that we calculate the drawdown with different time step, which is different value for this small t, and we add the drawdown caused by the well 1 and well 2 together, and by trying and error we will find a value, we will find a time that will cause the drawdown approximately to 1 meter to evaluate the time. Okay, so the idea is that. And in this equation, we already know the transmissivity this T here is equal to 500, and we also know the discharge rate for this well 1 and well 2. And we know this R is the distance from the observation well, and A is the storage coefficient. So everything that we don't know is actually this time t. So what we can do is to apply the equation here for the well 1 and well 2. So here I try different time step for different day, and we can apply this equation to calculate the corresponding u, and use u. For example, this is 0.04. We find 0.04 the well function is equal to 2.681, so we have 2.681 here. Then we apply this well function back into this drawdown equation, then we can get the value for the drawdown, which is 0.26 meter for the well 1. And similarly, we can do the same thing for the well 2. You calculate the u, you get the well function value, then you insert back to the drawdown equation to calculate the drawdown for the well 2. And in this case, it's 0.5. And then we can just simply sum these two drawdown effects from different wells together to calculate the total drawdown at the observation well. And in this case, 0.26 plus 0.5 is 0.76. And we just try different time setting, for example, day 2, day 3. And we found, okay, the value should be somewhere between day 2 and day 3. So we try 2.2 days for in this case, and we found the value for the summation of S1 and S2 is equal to 1. So we know that the solution for this problem is 2.2 days. So after 2.2 days, the drawdown will exceed 1 meter. Okay, so 2.2 days is our final solution. And the corresponding drawdown caused by well 1 is 0.33 meter, and caused by the well 2 is 0.67 meter. Okay. Okay, so let's move on to the next one. Problem 7.3.6. In this problem, we will use a similar concept, but this time the two pumps have different starting time. So according to the problem, the first pump will start at the time 0, but the second pump will start a day and a half after the first pump is started. So follow the same step from the previous problem. Let me draw the spatial diagram first. Write down the information first. So for the well 1 and well 2, we also have an observation well somewhere in the middle. And the distance for well 1 is 322 feet. and the distance for the well 2 is 279 feet. And the transmissivity is equal to 450 square feet per hour, and the storage coefficient is 0.0005. And at both pump with 270 GPM, and we will need to first convert the unit into the discharge, so we can apply it to the equation that I show here, which you can get it from the textbook at 7.28 and 7.26. This is the equation. If you want to know how those equation is derived, you can go to the textbook for that. But let's calculate the discharge first. So discharge here, we just do a simple unit conversion to the CFAs. CFAs we need to divide by 449 GPM. And we usually use per day to describe the discharge for the well pumping. So that's converts second into hour. Then we will get 1,660 cubic feet per hour. Oh, sorry, here we use hour, not days. Okay. Now we get all the information and we can follow the same step. We can just sum the drawdown caused by the well 1 and well 2 together. So let's start with the drawdown caused by the well 1. So again, we will need to calculate this coefficient u first. Then we will use this table 7.3 to find a value for the well function and insert into this second equation for the drawdown. Okay, so here the coefficient u for the well 1 is equal to 322 squared times ACE, which is 0.0005, divided by 4 times the transmissivity 450 times the time. And for the well 1, we are interested in 3 days after. So 3 days in 3 days is equal to 72 hours. So here is 72 for the well 1. And we get a value 4 times 10 to the power of minus 4. And for the table that I showed in the previous problem, we can get that a well function for the well function value for the well 1 is equal to 7.247. So we apply this value to the drawdown equation. We can get that this is 1,660. This is a discharge Q times this well function value 7.247 divided by 4 times pi times t, which is 450. This gives us 2.13 feet. Okay, so that's the drawdown caused by the well 1. And let's calculate the U coefficient for the well 2. This gives us 279 squared times base 0.005 divided by 4 times 450. This is the transmissivity. And the only difference is that the well 2 only starts 1.5 days after, so that's the well 2 only pump for 1.5 days, and 1.5 days equal to 36 hours, so that's why we have 36 here instead of 72 that we used for the well 1. Okay, so this gave us the value 6.01 times 10 to the power of minus 4. And again, from the table 7.2, from table 7.3, we have the value for the well function for well 2 equal to 6.842. And again, we apply the drawdown equation to calculate the drawdown. 6 divided by 4 times pi times 450. This is exactly the same as the well 1 instead of the value for the well function. And this gives us the value 2.01 feet. Then to calculate the total drawdown at the observation well, we can simply sum these two up. That is 2.13 plus 2.01. This gives us 4.14 feet. Okay, so similar concept, but the only difference is that they are start with different time. Okay, in the problem 3.8, we will view the drawdown problem with different variations. So in this problem, the flow rates of the well are changed. So discharge well penetrating a confined aquifer will pump at a rate of 800 cubic meter per hour for 2 days, and then the pump rate will reduce to 500 cubic meter per hour. The transmissivity is 40 meters squared per hour, and the storage coefficient is 0.00025. And we want to determine the drawdown at a location 50 meters away from the pumped well 3 days after the pumping has started. So again, I would like to draw a diagram to summarize the problem. So the time step that we're interested in is 3 days, but the flow rate, the discharge, initially is 800, but it will drop down to 500 after day 2. Okay. This is 800. And this is 500. And this is the pumping well. And we assume we have the observation well at a location 50 meters away from the pumped well. Okay, so in this problem, we will apply the equations 7.24 and 7.25 to solve it. So they are really similar to the previous problems for the drawdown. So the drawdown equation is basically the same, but this time we have different flow rate. Okay, so now I will just show you the steps to calculate this. I mean, to apply these two equations for the drawdown. So I will call the first 2 days the segment 1, and this day 2 to day 3 is a segment 2. Okay, so that means this larger that is showing this equation is 2, and Q0 is 0 because we assume there's no before start the pumping rate is 0, right? Okay, and the Q1, as we said, is 800. Q2 is 500. T0, T0 is 0, and T1 is day 2, right? So it's 48. Now we have the information and we just need to apply to the equation to show both. So let's start with the segment 1. For k equal to 1, that is the second one, U1 is equal to length. So plug in the value, we will have the distance r is 50 meters, like here, okay, times is the storage coefficient 0.00025 divided by 4, and the T, the transmissivity, is 40, given by the problem here, okay, and the time is 3 days, which is 72. Okay, so we have the value 5.43 times 10 to the power of minus 5. And we get that the value for the well function is 9.248. Okay. And for the segment 2, we have U2 equal to distance is the same, times 0.00025 divided by 4 times 40 times the last day, this period, okay, is 24. So this is the difference. Okay, so after we get the well value, then we can apply the drawdown equation. So is equal to 1 over 4 pi t q1 minus q0 times well function of 1 plus q2 minus q1 well function 2. Okay, then we can plug in the value. 1 over 4 pi t q1 100 minus 0 times 9.248 plus Q2 is 500 minus 800 times 8.196. So this is 300. And this gives us 9.83 meter of the drawdown at the observation well at day 3. Okay, so let's look back this equation a little bit more. So the idea is that we calculate the 3 days drawdown using this 800 discharge. Then here we minus 300 for the segment 2, which is after we calculate this rectangle, we minus this part, which is the reduced area, this part. So that is how we apply this equation to calculate the drawdown caused by this area. Okay. In the next problem, we are trying to categorize an aquifer using the field data. So in the previous problem, the storage coefficient and the transmissivity are often given, but here we have the measurement given and try to derive the aquifer characteristic. Okay, so here is the field data that we get, and the idea is that we will try to fit this data into the analytical solution to infer back the corresponding aquifer characteristic, which are the transmissivity and the storage coefficient, the T and X. Okay, so let's first plot those field data into an Excel, and this is the log T on the x-axis, and this is the drawdown on the y-axis. Okay, so the T, the aquifer transmissivity, is actually the slope of this line. No, it's not. I mean, the slope of this line is equal to 2.3 QW, which is the discharge rate, divided by 4 pi t. So we can calculate the slope and equal to this number to get this t value. Okay, or you can simply apply the equation shown in 7.42, and they are basically the same, but this delta drawdown here is is a drawdown difference between T10 to 1, because we have a low scale here. So this log scale between T10, the log 10 is 1, log 1 is 0, so they are the difference is 1 in the axis on this figure. So this is a different representation for what we just explained, which is the slope of this line is equal to this term, and you just reorganize that and you can get the equation 7.42, and now we're going to use it. So the delta drawdown between t equal to 10 and 1, which is this and this, that's 1.61 minus 1.09 is equal to 0.52. So and the Q here is given by the problem is 5.4. So you plug these delta A's back to this equation, you can get the transmissivity is equal to 1.9 square meter per hour. Okay. And then to calculate the storage coefficient, we'll use the next equation, the equation 7.43. It's a similar concept, and this T0 is the intersection of this fitted line at the axis. So in our case, T0 is equal to 0.0082. So again, you plug this T0 back to this equation, and you know the transmissivity, which you just calculated, is equal to 1.9 meter square per hour, and you also know the distance of this observation well, that is 18 meter away from the pumped well. So you can calculate this term, that is equal to 1.08 times 10 to the power of negative 4. After you know the characteristic of the aquifer, you can just apply another equation to calculate the drawdown after 50 hours. And this is equation 7.40 in the textbook. Now you know everything. You know the Q, which is 5.4. You know the T, that is equal to 1.9. And you know the storage coefficient is 1.08 times 10 to the power of negative 4. and this small t is equal to 50 hours. Then by applying this equation, we can get the drawdown is 1.97 meter. Okay, the alternative way is that you can calculate the drawdown by using this figure, but I will leave that to you because you need to calculate the log of 50 hours, so log 50, and you can use that to find the corresponding drawdown at the y-axis using this line that you estimated from your field observation data. Okay, so this is how you characterize the aquifer and use this field data to calculate the drawdown. Okay, let's move on to the next one, the problem 7.5.5. So we have a system set up like this. And this is the ground. And we have a river here. And the factory is pumping. Have a pump well 5,660 feet away from the full penetrated river. So assuming that the well is here and the distance is 5,660 feet with the flow rate equal to 1.5 CFS. And we also have an observation well located between river and the pump well, and it's assuming to be here, that is 100 feet away from the river. So this part is 560 feet. Okay. And we found a registered drawdown of 0.333 feet in this observation well. The ACE, let me just write ACE, is equal to 0.333 feet at the observation well. Okay, so assuming the surface of the river is somewhere here, and normally the drawdown curve should be asymmetric, but the river will recharge it. So that's mean the drawdown curve is steeper at the right hand side in my plot. And here is what we observe. And to calculate these, we will need to use the image well. That is 5,660 feet on the other side of the river boundary. So we have an imaging well here for the recharge. And the distance is also 5660. So it's like the mirror of the pumped well. And okay, so this charge is this image well is for recharge with the same Q. That's 1.55 CFS. Okay, then we will use this system to calculate the drawdown by using the equation 7.12a. So now that's set. The drawdown at the river is 0. Okay. So if we apply this equation, this A's will be 0, and our observation drawdown on the observation well is 0.333. Okay. And the QA is 1.55 for this well. Okay, this is the pumped well. Okay, 2 pi t is the variable that we want to evaluate times log the RAO is 5,560. That's the distance between this pumped well and this observation well, divided by RA, which is 5,660. That's the distance between the river and pumped well. And we need to plus the third term. That is our imagined well for recharge. So with the same amount of recharge, but the sign will be different. This is minus 1.55 divided by 2 pi t times log ROB. So this is B, this is A, just to refer to this equation, is 5,660 plus 100. So it's 5760 for ROB, and RB is just a distance from the river, right? So it's the same as the RA. It's 5660. Okay, so the only unknown in this equation is this transmissivity T. So you can solve that. And here I will give the answer. T is equal to 0.0262 feet squared per second. Okay, so in this problem, we need to understand the concept of imaged well. And if you want to know more about this concept, please go to the textbook and find the location at this equation, which is equation 7.12a, and we'll see how to set up this system. And here I just basically demonstrate how do you set out the system for this specific problem. Now, let's move on to the last problem for this entire semester, that is the problem 7.9.1. We need a centrifugal pump to dispose of the water seeping through the earth leaf depicted in the figure down here. And we will use the flow rate shown in this figure to estimate the seepage rate in units of GPM, gallons per minute. And the information that we know according to this problem is that the water level behind the leaf, this H, is 30 feet. And the leaf itself is 980 feet long. The permeability coefficient of the soil is 7.5 to the times 10 to the power of -6, and this permeability coefficient have the notation K. And the porosity is 0.4, but that is not really required information for this problem. So the flow rate, the concept of flow rate is that in each grid, the delta Q is the same. Okay, so you have delta Q flow through here, delta Q flow through here, to here, to here. So this N value is how much segments, how much row you have in this flow rate. So in this figure, we have 4. So M is equal to 4. N is the column in this flow rate. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So till here is 30. So that says this end is 30. Okay. So we can apply the equation shown on the screen here, the equation 7.56, to estimate the total flow over this flow rate. So we know that the K, the permeability coefficient, is given is 7.5 times 10 to the power of -6 times M divided by N, that is 4 divided by 30, and H is the height, which is 30 feet. And this gives us the number 3 times 10 to the power of -5 CFAs. Oh, CFAs per feet. Okay, and to evaluate the total seepage over the full length of the leaf, we need to eliminate this per feet. So to do that, the Q represents for the seepage rate is Q. Let me just write a number. This small q times, and I also write the unit here for your reference, times the length of this leaf, that is 980 feet. So we eliminate this result, but the problem asks us to present the unit in GPM. So let's do the unit conversion from the cubic feet per second to GPM. This is 449 GPM per CFS. So GPM per CFS. So now we have a seepage rate equal to 13.2 GPM. So just to verify that, let's cancel the unit out and cancel the unit out. Okay, so our unit is GPM. So that is how you use the flow net to estimate the seepage rate in this problem. Okay. So hope you enjoy the recitation for this semester, and see you next week on the recitation in person.